I've written up all 6 of the inverse trig function formulas here, and we're just going to use them. Now, I want to say something about it. It looks like it's a lot to remember, and it kind of is. But first of all, I wrote them up in chain rule format, so it's with a u. You have to think about this u as being some other function, like, for example, our first problem, inverse secant of x squared. If we're going to take the derivative there, then our u is going to be x squared. So that's the first thing. So I wrote them all up like that. And the second thing you might notice if you look at them carefully, it's really only 3. It's not 6. Because sine and cosine, they're the same but for a minus. So the cofunction is the same as the function, just a minus. So of course, because it's the same thing for the actual trigonometric function, like the derivative of sine, derivative of cosine, right? It has the cofunction comes with a minus. For the inverse, it's going to be the same. So it's not like you're remembering 6 things. You're really remembering 3 things. Okay? So for inverse secant, it's 1 over u times square root of u squared minus 1. So let me write dy dx instead here. So I'm going to do 1 over my u is x squared times the square root of u squared minus 1 times the derivative of what's inside, right? Because these are all chain rule problems, really. So if I clean this up, I end up with this. Right? So this is not very hard. You do have to remember that you want to put that whole u into every u or x, right? Because if you look it up, typically it just has the x. So you want to put that in for all of them. Now, let's do a couple others. Just real quick, I have a few here that are sort of useful to look at. This one, natural log of inverse tan of, what is this, t to the 4th? Okay, so dy dt, this is a couple chain, like a double chain rule, right? My outside function is natural log, so I'm going to do 1 over this, inverse tan of t to the 4th, times the derivative of everything that's in the parentheses, which is then inverse tan of t to the 4th. Right? So that's first using the derivative of natural log. Now, I have to take this derivative. So for inverse tan, it's 1 over 1 plus u squared. So it would be 1 over 1 plus t to the 4th squared times the derivative of my u. So if I work this out all the way, I've got this here. My bottom is here, and then this would be 4t cubed up there. So that's the derivative. Okay. Let's do another one. Here I've got inverse sine of x times natural log of x. All right, well, this one actually isn't a chain rule at all. This is just a standard product rule, right? So I've got dy dx should be inverse sine times the derivative of natural log plus natural log times the derivative of inverse sine. So that's not hard, right? So this would be inverse sine of x. The derivative is 1 over x here. And then this one, I've got natural log, and then the derivative of inverse sine is going to be the square root of 1 minus x squared. So they're not all terrible, right? It's just important to kind of recognize what you have to do. Okay, I'm going to do one more that is a little bit, it's not even that bad, but you know, this is one where we have to do a multiple chain rule kind of thing. E to the inverse cosine of x squared. Let me start out with a inverse something of x squared. I don't know. All right. So here we have the outside function being e, right? So if the derivative is just e to the u du dx, so d dx of inverse cosine of x squared, right? So I have e to the inverse cosine of x squared, and then inverse cosine is going to be this guy. So I've got minus 1 over the square root of 1 minus x squared quantity squared, right? Because it's 1 minus u squared. And then times the derivative of what's inside. So I'm not going to write that as a separate step. Okay. And then you can clean this up a little bit, but it's pretty much like there's not a whole lot you can do with that. So I'm just going to stop these there because they're fairly straightforward. It's just a question of knowing the formula and using the formula.